Recording is rolling. It is Wednesday, September 25th. We're going to solve as many textbook puzzles as we can today. And since I've been through a few classes, how it's going to pace out is pretty much these three right here. You guys remember this page I gave you a few days ago? So for context, we got chapter 4 is forces in 1 dimension. Eventually, we'll get to chapter 5, forces in 2 dimensions. But today, we're going to do these 3 puzzles in class, which really each of these has multiple parts. So really, it's like 11 or 12 puzzles, but we'll just focus fully on these. Okay. Now, what else I got on this agenda? All right, I wrote this morning before the news. I said if there's school tomorrow, then of course we'd be doing that Atwood lab that I've been telling you guys about. Right. But you guys know by now there's no school tomorrow. There may or may not be school on Friday. I don't know. So okay. See you there. So if there is school on Friday, I think I'll try to fit in at least part of this lab on Friday. If there isn't, then we'll have to bump this to next week. Guys, since we're gonna have some at least one or possibly more hurricane days off, you guys think it's a good time to definitely check focus, make sure you got everything in, catch up on any work you need to catch up on this class, other classes. I'm telling all my classes too. I'm still waiting for some projectile quizzes to come in, right? But got to do that, right? Also, this page that we're working on today, I don't have a due date for yet because I want to solve a bunch of these with you guys in class. Plus, with hurricane and whatnot, I don't know exactly how it's all going to pace out. But let's get going. All right, so the ones I'm going to have you guys turn in and I'm eventually going to grade. We'll collect these from you guys, are just the ones that I circled. So that's the ones we're going to focus on in class. If you want some extra questions and extra practice, then of course you can start looking at the ones that I didn't circle. That's a good opportunity too. We're just going to focus on the ones that I circled. So number 58, you toss a ball straight up in the air. Hey, toss the ball straight up in the air. This is a scenario that you guys have seen a bunch of times. But now we're interested in forces, dynamics. Hey, draw a free body diagram. You guys have drawn a bunch of these, free body diagram on the ball at 3 points in its motion. On the way up, at the very top, on the way down, identify the forces on the ball and their agents. And then there's a couple of follow-up questions. So let's start with that. The free body diagrams for this ball in motion. Zoom out, you guys can see this. Okay. So you guys write chapter 4, and eventually we'll get to chapter 5, but not today, puzzles. Right. So eventually you guys can staple these together and then turn these in probably a week or 2 from now. Right. You guys write your name on your paper. You guys write name. And then we're starting at number 58. This is chapter 4, number 58. Right? Are we good? Okay. So if I draw a scenario out, something like this, I take a ball, throw it in the air, goes pretty much straight up, coming straight down. At some point, it's going to be at the top. At some point, it's coming back down. Okay. So maybe I pick those 2 points, and I want to know what's the forces on those points. Okay. So let's bring this out here. So this is here, moving up at the top, and then moving down. So let's get it right out here. I got a ball. So it's little baseball stripes on this. Okay. At one point it's moving upward, so throw a little velocity arrow just for context. Although, guys, are velocity vectors part of free body diagrams? No. What kind of vectors are part of free body diagrams? Force vectors. Yeah. I drew a center mass dot for each center. You guys know this is like picture 1, 2, 3. Just bring them right here. Going up at the top and come down. Okay, here, I'll even label it. I should label it. Moving up at top and then moving down. All right, there you go. There's 1, 2, 3 scenarios. Okay. All right, so force vectors. Right. What's one force vector on this ball right here? Gravitational force. It's weight. And guys, which way does weight pull? Straight down. So get a vector going straight down. Could I label that? What could I label that? mg is a good call. Mg, that's what I usually do. Mass times gravity field. Right? If you see F sub g, force due to gravity, that's okay too. Right? Now, oftentimes in this class, probably more often than not, we tend to ignore air drag, right? Well, let's do this way. We're going to ignore air drag for a moment, and then we'll go back and add air drag later. But for now, let's say if air drag is either negligible or non-existent. Right? Would there, in that case, be any other forces on that ball? Does there have to be an upward force? Is there an, guys, the ball's moving upward? Is there an upward force on the ball? No. Now there was when it was in your hand. So while you were throwing it, there was an upward force from your hand. Right? But once it's just moving upward, yeah, there's no upward force. Right? How about at the very top? Guys, at the very top, what forces are on the ball? Yeah, gravitational forces, weight. Is there anything else? Nope. How about when it's coming down? What force? Weight. Right. So boom, boom. Hey, as long as you ignore air drag, are those three free body diagrams exactly identical? FBD, free body diagram. Yeah, they're all exactly the same. They're indistinguishable. They're all in free fall. Right? Now, are you guys ready to go back and add some air drag? Right. Oh, sorry, one more thing right before we get to air drag. Right. Suppose I throw the ball up and it takes like 3 seconds to go to the top. How many seconds does it take to fall back down? Another 3 seconds. So it could be 3 seconds up, 3 seconds down. That'd be symmetrical, right? Hold on to the idea because we're about to add some air drag. That's all going to change, right? Air drag time. Guys ready for some air drag? Oh, now when the ball is being thrown upward, it's moving upward. Which direction does the air drag point?
Mind if we borrow Aiken for a yearbook?
All right. So yearbook, yeah, go ahead. Okay. Guys, which way does air drag point? Is air drag opposite of the motion? So if the ball's moving up, is air drag down? I think it would be. Right. Here's how I'm gonna do this. Oh, I'm gonna do a little side notch maybe and draw also a downward vector. Right. Now I'm gonna guess probably air drag is relatively small compared to its weight. It doesn't have to be, right? But you can think of it. So I'll label this F sub drag. They say it like relatively small force. Is that right? All right. So then is that okay? All right, then the ball gets to the top. No, we are considering that there is an atmosphere and possibly air drag. How do I modify this picture of the ball at the top? Does it need anything else? No, that's it. It's already done. Because here's I do have a poster with a drag force equation on it. Right? So drag force, here's the full equation. But if I just kind of focus on these variables, drag force is proportional to speed squared. Well, guys, what's the speed of the ball at the very top? 0. So there's no drag force. Right. And then the faster the speed, the more drag force. But yeah, but 0 speed against the air, 0 drag force. So we're done with this one anyway. Right? And then when the ball's coming back down, which way does drag force point? Opposite of the motion, which would have to be upward in this case, wouldn't it? So F drag would go like that. There it is. There's what the drag force is in. Right? Ball goes up, goes back down. Okay. All right. There was a follow-up question I asked is about the time to go up and go down. Right? So there was like, if there was no air drag, it's the same time up as down. Right? But if you include the air drag, does it take more time to get to the top or more time to fall back down? So show of hands, what you guys are thinking? Right? It's not the same anymore. So it'll be different. Right? So you guys got two options. With the air drag, does it take more time to get to the top or more time to fall back down? So show of hands. How many guys think with the air drag, it takes more time to get to the top? How many say it takes more time to fall back down? Yeah, that's what I would say too. It takes more time to fall back down, right? Here's why. You guys see moving upward, there's going to be a huge downward force. Like if the weight of the ball was 10 newtons, suppose you have 2 newtons of air drag, that's a total of 12 newtons. The ball's slowing down in a hurry. Right? But when it's falling back down, you guys see maybe 10 newtons minus 2 newtons could be like 8 newtons net force divided by the mass of the ball. It's accelerating kind of slowly, right? So put its motion together, it goes like this. Like, so it's just stop in a hurry and then kind of drifts down more slowly. It's kind of exaggerated, but it takes more time to fall back down. Okay. They asked some other questions about the situation. Let's check this out. Identify the forces acting on the ball. Okay, which we just did, and their agents. So what what object is pulling on the ball, causing it to have a weight? The Earth, right? Right. So you guys were like object A, object B, right? you know what? This force mg, this is the Earth pulling the ball down. Does the ball also pull up on the Earth? Yeah, it has to, right? Right. But guys, which force is bigger? The Earth pulling the ball down or the ball pulling the Earth up? Huh? What does Newton's third law say? It's the same force, right? Now, I did not draw the Earth being pulled up because these free body diagrams, you tend to just focus on a single object, right? But don't forget, there's another object that has an equal and opposite force going on with it. Okay, and then how about this? The drag force, that's from the air, of course, right? This is the air pushing against the ball. Does the ball also push against the air? Yep, with an equal and opposite force. Yep. All right, so also got here, that was all part A, right? So part A. Part B, what's the velocity of the ball at the very top? So here, this is all part A. Right? Part B, velocity at the top is how fast? 0 meters per second. Of course, that's all, I guess, part of this scenario, right? Velocity at the top. Okay. Part C, what is the acceleration of the ball at the top? Acceleration at the top. And it's not 0. So okay, here, let me kind of route these around. This is all referring to the scenario right here. Guys, what's the acceleration of the ball at the very top? 10 meters per second squared. Here, I'll give you guys 3 possible options. You could say G, you could say 9.8 meters per second squared is okay, but I usually round that to 10 meters per second squared, right? It's from a dynamics point of view, isn't acceleration equal to force on mass? Right? Well, I should say net force. So some of the forces on mass, but at the top there's only one force, it's weight. So wouldn't that be mg and then divide by m? Hey, that gives you g. There you go. There you go. Right. So if it's in true free fall, if there's no air drag or negligible air drag, yeah, it's accelerating at g from the moment after it leaves your hand to the moment right before it crash lands. Okay. And if there is air drag, then this is specifically true at the very top where there's 0 velocity. All right, you guys good on number 58? Right, there it is. There's A, B, and C for 58. Boom, boom, boom. That's good. All right, next one, number 69. Assume that a scale is in an elevator on Earth. Ooh, here it is, scale, elevator, Earth. Right. What force would the scale exert on a 53 kilogram person standing on it during the following situations? So a bunch of scenarios, A, B, C, D, E. Let's look at them all real fast. We got the elevator moves up at constant speed. The elevator slows at 2 meters per second squared while moving upward. The elevator speeds up at 2 meters per second squared while moving downward. The elevator moves downward at constant speed. The elevator slows to a stop while moving downward with constant acceleration. I'm going to add a little bit to that. I'll call it 2 meters per second squared also, just to be consistent with the other scenarios. So moves downward, slowing to a stop at 2 meters per second squared. Right, so we got 5 different scenarios. Those all sound a little bit different, huh? Right. I wonder if some of them are kind of the same. We're gonna see. So here we go. Number 69. Right, you guys wrote on your paper. Eventually you'll turn this in, of course. Right. So let's start with part A, which is elevator. Let's just say moves up at constant speed. Moves up at constant speed. You could also say constant velocity. Its direction is not changing either, so that's okay. Say constant velocity. Okay. I'm gonna leave a little space here for a certain reason, but let's get a diagram of an elevator going on. Elevator. Here's elevator. Right. We've got a person standing in the elevator on a scale. So, this guy's standing on a scale. Look at there, standing on a scale. Okay. Now, I know the mass of this person is 53 kilograms. 53 kilograms. Okay. And we're in Earth gravity, which I'll probably go ahead and round to 10 meters per second squared. Okay. let's do a center of mass dot on this person. All right, let's do a free body diagram. Free body diagram. Okay. So moving up at constant speed, so constant velocity. But I'll put a little arrow out here just for context. That's not part of the free body diagram, but let's move it. Guys, moving up at constant velocity. So we guys have, all right, what's one force on this guy? Yeah, his weight. The weight pulls straight down. Okay. So that's a downward vector. Okay. I call it mg. Right. Oh, and if you tag a number to that, how many newtons is that equal to? About 530. 530 newtons. Because m times g is weight. Here's his mass, 53 kilograms. G is, let's call it 10 meters per second squared. That's 530 newtons weight. Is that true? Right. Now, is that the only force vector? No, because if it was, he would be in free fall. So what other force is acting on him? The normal force from the scale. Normal force from the scale. Okay. So is that going to be upward? Okay. Now, guys, how big should I make the normal force compared to the weight? Should it be longer than, shorter than, or the same magnitude? Same magnitude. Yeah. How'd you know? How'd you know it was same magnitude? Yeah, exactly. Constant velocity. Constant velocity means there's zero acceleration. So if I do a little bit of math out here to back this up, got some space here. See what I do. I could say Newton's second law of motion. The net force, which a lot of times I'll write as like this: the sum of forces. It's the same thing. Because if I say net force or sum of forces, those are the same thing. Right? Equals mass times acceleration. Right? And in this case, the net force, well, it's a difference of two forces. It's the normal force one way minus his weight the other way. That's going to be mass times acceleration. Right? Right. But if acceleration is 0 meters per second squared, this whole bit just goes away. Therefore, normal force is equivalent in magnitude to the weight because you just add that over algebraically. Okay. If this was 530 newtons, then the normal force is also 530 newtons. Okay. All right, guys good? Guys good? Oh, you know what? That was part A. The elevator moves up at constant speed. So you guys good? Moving at constant speed? Right. But wait a minute. What if the elevator was moving down at constant speed, moving down at constant velocity? Would that be the exact same free body diagram and the same rating on the scale? Which I think was one of the other scenarios. Let's check through here. Option D, or part D. Part D. Look, moves downward at constant speed. Is that exactly identical, same numbers, everything is what we just did? The only thing I have to do is reverse the slow velocity arrow, but everything else is the same. The forces are the same, the math is the same, the normal force on the scale is the same. Right? In fact, if you're standing on that scale, could you tell if you were either at rest or moving up at constant velocity or moving down at constant velocity? No, there'd be no way to know. Right? You could not feel the difference. So I'm going to say D. I'll just throw D right here. Elevator moves down at constant velocity, or say constant speed, but directions change the exact same. So even if you reverse the velocity, same thing. Right, so got part A and part D. Check. Just ready for next part. Right, so there's A and D, and it's all the same. Right. Oh. Around here. I'm going to do this a little out of order for a certain reason. You guys can see. It'll make sense by the end. Let's do part E. Part E. All right, we'll go back and hit B and C later. Okay, so 69 part E. All right, and this is elevator slows to a stop, moving downward. Okay, so moves down, slows to stop at this I'm going to make up. Acceleration equals 2 meters per second squared, just so that it matches the some of the other scenarios, right? So just so we got a number. All right, let's do a free body diagram for this scenario. I got the elevator, this guy, elevator, sand on his scale. There's a scale right there. Give him a center mouse dot. Oh, I remember his mass was 53 kilograms. So it's 53 kilograms. Okay, now I'm going to have the elevator moving down. So velocity is going down, right? But maybe that doesn't even help us with anything, right? We don't have to think about air drag or anything like that. So, okay. But the important point is this, how it's accelerating, right? So guys, moving down, slowing to a stop. Let's think about this. Did you guys the other day, remember you guys did the bunch of mini labs? I gave you guys some spring scales and a bunch of mini labs. And one of them you were accelerating it up and down. Think back to that part right there. Okay. Let's get some forces on the sky. What's one force on the sky? His weight. Yeah, let's start with his weight. Okay. So I could call it mg, which is how many newtons? 530, let's call it. 530 newtons. There you go. Okay, so we got that. Okay. Is there what kind of force from the scale? Normal force. Right now, here's the part. Here's the tricky part. Right. Is the normal force less than or greater than his weight? Greater? Yeah. So I should draw a longer magnitude force vector and label it normal force. Right. And we got to get a numerical value for this too. Right? Isn't that actually what the scale reads? The scale's about to tell them some force reading. It's really telling them the normal force. You guys think it's going to be more than 530 newtons? Yeah, right. Okay, so guys, if you're moving down, slowing to a stop, I'll add a detail here. That is an upward acceleration. Upward acceleration could be one of two things. It could be you're moving up faster, or it could be moving down, slowing to a stop. And if you're inside the elevator, those two scenarios feel exactly identical. Therefore, upward net force. Therefore, the normal force is greater than the weight. So let's do some math on this one. Okay. Can I do Newton's second law of motion? Say net force, okay, which is equal to sum of forces, if you like. Right, same thing. Equals mass times acceleration. So we got that. Right. Now the net force, or sum of forces, if you like, can that just be could be the difference between these two because one's going up, one's going down? Okay. So I'll do it like this. I'll say that's the normal force minus his weight is equal to m times a. Right? Is that right? Everybody good? Very good. Okay. Next thing I'm going to do, I'm going to split my paper right here. I'm going to solve the rest of this two different ways. Okay. So up to you how you want to do this in your paper. I'll solve this in terms of variables. We're solving for the normal force, and I'll also solve with numbers. Just plug some values in. Okay. So see, if I solve in terms of variables, it's all just algebra. Can I take the mg and just add it over to the other side? So the normal force equals mg plus ma. If I plug the numbers in, it's going to look like this. Normal force I'm solving for minus, hey, mg was how much? How many newtons? 530. 530 newtons results in a mass of how many kilograms? 53. Right. Accelerating at how many meters per second squared? 2. Right. Oh, now one more detail. Should it be +2 or -2? Let's get some directions going on. Right. Now it looks like how I set up the net force is I'm saying normal force is up is positive and the weight I'm calling negative. You guys see that? So it looks like up is positive and down is negative, right? And if that's true, see, he's moving down, slowing to a stop. That makes acceleration upward. So should acceleration be positive because acceleration is upward? Right? So is that +2 meters per second squared? I'm just saying plus just to emphasize that it's positive. You could just say 2. Okay? Right? Because you have to be careful. Sometimes you got two different directions going on. You got to be careful about that. Guys, does this come out to like 106 newtons? You see? And then could you just add the 530 newtons over? So normal force is whatever 530 plus 106 is. I think is that 636, I think. 636 newtons. Right? Does that look about right? Right. Okay. Now, what about my variables? Now, if you like, you could throw in one more step. I could factor in the mass out. So m times g plus a. Right. Let's see if this works. Normal force is, I got 53 kilograms. I got a gravity field of, let's call it 10 meters per second squared, and accelerating at 2 meters per second squared. 10 plus 2 is 12. What is 53 times 12? Moment of truth. Hey, it's the same thing. It's the same thing. Physics wins again. Oh, yeah. 636 newtons. Oh, yeah. Oh, yeah. So whether you solve in terms of variable, see, an advantage in solving in terms of variables, maybe this could be a really good tool for your toolkit, is now you have a master equation that can solve any of these. So like the mass of anyone riding any elevator on any planet at any acceleration, you got some master equation. Right? First, if you pop in the numbers, you'll still get the right answer. Just it's specific to that situation. Right? You guys good? And you know what? Everything. The reason I wanted to start with part E, after is that I have a poster that's specifically this situation. Hey, isn't that what we just did? Isn't that what I just derived right there? Right? Now, this is an upward accelerating elevator. Elevators accelerating upward. Look at that. Normal force is greater than the weight, right? And it works out exactly like I just showed you guys. Okay? Now, what if the elevator was accelerating downward? You guys think there might be some signs that are different? Maybe I flip some positives with negatives or something like that. And how do you think the equation would be different at the end? Yeah, instead of g plus h, g minus a. Exactly. Right. So I have another poster that just lays out these different scenarios. Here's upward accelerating. You guys just saw that. Right. Here's non-accelerating, where just the same. Oh, I switched this to tension in the elevator cable. That's the same math. Right. Oh, and here's downward accelerating. And, just like you guys just said, it's going to flip to minus. If you do the proof, that's just how it works out. Right. So you guys ready to go back and hit B and C? I wonder what scenario B and C are going to be. Let's see. So part B, the elevator slows at 2 meters per second squared while moving upward. So let's do this. 69B, right, and I'll leave a little space to go back and put in C later, is moves upward and slows at 2, well, okay, here, so an acceleration equals 2 meters per second squared, right? Okay, if you're moving upward and slowing, then which direction is the acceleration? But let's do an extreme example. Suppose you take a ball and you throw the ball straight up in the air. Now, after it leaves your hand, is it moving upward and also slowing down? Which means it's accelerating which way? Down. Right? I mean, this is after you release it, right? It doesn't gravity pull straight down. Right? I'm throwing the word down right here, right? Because acceleration is a vector, so it needs a direction. We're talking about 2 meters per second squared down. That's what moving upward slowing is. Okay? Now the elevator is a less extreme case of that. It's not in pure free fall, right? But so let's take a look at free body diagram. Let's do elevator. Put our guy back in here. Because remember, this guy has a mass of 53 kilograms, just like he has all along. Stand on a bathroom scale. Right. Right. Give him a center mass dot. All right, force vectors time. Does this guy still have the same weight that he's had all along? So I can do here. Let's do mg. Is that still 530 newtons, just like it's been for like all along so far? Okay, so same weight. I think it's probably support from the scale. Okay, now guys, for moving up, slowing to a stop, should the support force from the scale be larger than or smaller than the 530 newtons? It's gonna be smaller. Right? And I'll draw this kind of exaggerated. I'll draw it pretty short, but Yeah, so it's kind of exaggerated, but you guys see the normal force is smaller than his actual weight, right? If you were in this exact situation, you're riding an elevator up and it's slowing to a stop. Suppose you're at the ground floor, you're going up to the 5th floor, and it's like slowing and coming to a stop at the 5th floor, right? Temporarily, you feel really what? Really light or really heavy? Really light. You sure do. Right. Let's do the math on this. Here's Newton's second law of motion. Net force equals mass times acceleration. Here the net force is, let's say, normal force upward that we're solving for. Gotta know that is that minus the weight downward results in mass times acceleration. Right. But let me do one more thing. Right. I'm going to modify this a little bit. If I want just let's say a positive number for acceleration, something like that, positive number, right? But I want to specify that it's downward. How can I change this to specify this is downward? Can I throw in a what sign? Negative? Can I throw in a negative to say it's down, just to take care of the word down? Is that okay? So negative can mean down. Is that right? Okay. Let me go ahead and finish this off the same way I did before. I'm going to split my paper and solve this in terms of variables and solve with numbers. Okay. So with variables, can add the mg over and get the normal force reading from the scale is mg minus ma. And if I like, I could factor the mass out, get m times g minus a. Hey, that's that is exactly what you guys said it was going to be. You guys said it should be that, and it sure is. It's like that. Okay. What about with the numbers? So with the numbers, I'll do normal force. I'm solving for. Okay, here's minus the weight. It's 530 newtons. Right, equals. Right, and then I got a negative. I got 53 kilograms, and then 2 meters per second squared. And I took care of the word down by also including that negative right there. So that's taken care of. Okay. So is this right here like negative 106 newtons? Okay. If you add the 530 over, let's see what that's going to come out to. It's 530 minus 106 is 424. Ooh, hey, look at that. The scale rating is less than his actual weight. So if he was just standing out on the sidewalk on the scale, he'd say, oh, I weigh 530 newtons. But inside this elevator that's moving up slow into a stop, he does feel light. He's only 424 newtons, he'll say. Okay. Well, let me check my math over here. What is 53 kilograms times 10 minus 2 meters per second squared? So it's like 8. What's 53 times 8? Is it? Hey, that's 424 newtons. Oh yeah, 424 newtons. It's the same thing. Same thing. Again, tool for your toolkit. If you can solve in terms of variables, you got some master equation that can solve anybody's elevator. All right, guys good? All right, one last part here we haven't done yet. You guys ready for part C? Part C? Part C. The elevator speeds up at 2 meters per second squared while moving downward. So goes down faster, faster, faster. Hey, guys, if you're moving down faster, 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 you're accelerating which way? Would that be down? Right? In fact, an extreme case would be you just toss something off a cliff, right? That's accelerating downward for sure. Okay? Now this elevator isn't polar, but yeah, overall it's tending that way. You guys think what we just did is also the answer to that? So we did part B, but this is also part C. Moves downward. And speeds faster at acceleration is 2 meters per second squared. Of course, this would also be down. Yeah, this is an identical scenario. So if you started at the 5th floor of a building, and then you say, I want to get down to the ground floor, and then the elevator doors close, and the elevator starts to move down from the 5th down to the 4th floor, you feel something more like this. You feel light for a brief moment. Everybody good? Good. All right. We're going to do one more scenario today, and that'll bring you guys to my other classes. All right, guys ready for number 73? You guys ready to jump off a tower? Number 73. A 65 kilogram diver jumps off a 10-meter tall tower. Find the diver's velocity when he hits the water. Oh yeah, there's water. Yeah, surprise. And the diver comes to a stop 2 meters below the surface. Find the net force exerted by the water. All right, so one question at a time, one at a time. Number 73. All right, here, I should draw this out. Let's get a 10-meter tall tower. So here's this guy standing up here. He's about to dive off. Let's put some water down here. Water. Right. I'll say height equals 10 meters. Right. This guy's gonna be diving down into the water. And then there's a second part of this question we'll get to later. It says, suppose he goes down 2 meters before he comes to a stop. Right. So I'll call this vertical bit right here. I'll say y equals 2 meters. So that we won't get to that until part B. Right. So there's a part A, he's falling to crash into the water with some crash speed. I'll call this V splash. Right. And then the water is gonna bring him to a stop 2 meters down below. Like that. All right. What is the diver's velocity when he hits the water? Oh, you know what? Guys, does this sound kinematic? Like kinematic motion? Right? Huh. Well, I think this is a good review question right here. For back to, I bet you guys could have solved this like 3 weeks ago. Let's do a little tax VV table. Time, acceleration, displacement, initial velocity, final velocity, because those could be the 5 variables we could be juggling, right? And you need to be able to identify how many of those to solve any of these. 3, right? So what do you know, guys? What's one number you know? X. That could be what? 10 meters, right? So we got a height change at 10 meters. So this guy's going from the edge to the splash. Right? Oh, I guess we're solving for V splash. So that's like this right here. We're solving for that. Okay. What else do you know? Acceleration. Is it okay if I call it 10 meters per second squared? Do that. Okay. What else do you know? Or could you reasonably assume? Initial velocity could be how much? 0 meters per second. Like if this guy just kind of steps off or something. Okay. All right. All right. You guys remember those 3 kinematic formulas that are also on that poster in the corner over there? Okay. Which one is going to solve this the fastest? Maybe he doesn't mention time. Which one doesn't mention time? The third one? Third one? Right, let's do it. Right. You could use the first and second in a system of equations. It'd be a lot of paper and a lot of time, but we're gonna do the third one. Vf squared equals V naught squared plus 2ax. Third kinematic formula right there. Let's modify this a little bit. So this V naught is 0, so squared is 0. It just goes away. Goodbye. We're solving for or calls V splash. We're solving for V splash. I'd like to know. That's being squared here. Okay, and then guys, is it okay if in place of the A for acceleration, can I call it G for acceleration due to gravity? And in place of X for general displacement, is it okay if I call that H for a height of the tower? Okay, like 2GH. Okay. Now this one I want to solve in terms of variables first, because you can do that in one step at this point. Guys, what's the one step you need to solve for V splash? What do you do to both sides? Square root. Right. So V splash equals square root 2GH. You guys have seen this before. If you know the height of a tower and you say drop a ball off a tower, right? The speed that it crashes vertically is square root 2GH. Okay? You're going to see this again. I'll tell you where you're going to see this again in this class. A few weeks from now, we'll do conservation of energy. It'll be a different process, right? And you're going to see the same question. You drop a ball off a tower, how fast does it crash? We'll go through a completely different mathematical process. And this is always going to be the answer to that question. Next semester, we'll bring in fluid dynamics and Bernoulli principle. And suppose you have maybe a water tower and a tube of water and it goes down to ground level. And the water's spurting out at some speed. Guess how fast the water will be spurting out of a vertical tube? Square root 2GH. So this is going to show up all over the place in physics. Right? So now we got that. Let's go ahead and plug in the numbers. B splash equals square root. Popping my numbers here. Got a 2. I got a 10 meters per second squared. I got a 10 meters tall cliff. Right. So all grouped together. Right. Oh, do you guys see how I extended my square root bar over that entire inside expression? Right? Is it like I didn't stop it halfway? It's the whole thing. Right. All right, it's calculator time. Calculator time. Right. Guys, let me give you guys a little heads up here. I'm going to plug this into my calculator incorrectly. I want to see who can catch my mistake. So second square root. Can you guys pull up a square root? That's okay so far, right? Square, second square. I got a square root. I got a 2. I got a 10. I got a 10. Let's see. What is this guy's crash speed? And it is 141 meters per second. That's over 200 miles an hour. Ah, you guys think this guy's crashing at 141 meters per second? No, that's way too fast. What did I do wrong? Parentheses. Exactly. Right. Now, guys, different calculators are different. It's good to know how to communicate with calculator. This model, which everybody has, as soon as you close that parenthesis, it stops square rooting. So all this did was take the square root of 2 and then like multiply by 100. Okay, that's what. But there's a quick fix. You guys see these keys right here? These arrow keys. Scroll up, scroll over, second, insert, open parenthesis. Okay, now you're good. Very good. This calculator will automatically close the parentheses anyway. Not all models do. So if you have to, you can close it. Right. 14 meters per second. That looks a lot more reasonable. So B splash equals 14 meters per second. All right, 14 meters per second. That looks about right. I can believe that. You know what? In the side here, I'm going to say equals 14.14 meters per second. Or if you like, you just do a square root of 200 meters per second. Right? Because there's a part B to this question, and it's going to carry over from that information. So if you save a bunch of precision in your digit, save a bunch of precision, a bunch of digits, then you can save all your rounding for the very end, and you'll have better answers at the end, more accurate. Okay. All right, so you guys good so far? That was all part A. That was all part A. We're going to do part B, and then that'll be our pause point for Hurricane Day coming up. You guys ready for part B? Part B? Okay. Now, part B is this. You guys remember he splashes in the water and comes to a complete stop 2 meters down? All right. So I'm going to draw that. I'll blow that up right here. So this is 73 part B. All right, so here's the water line. This water line right here. You know, when I was in college, I think what they did was to represent a water line, they would like do an upside down triangle. If you ever see that notation, I think that's what they did. Because you could just draw it flat. It's got a little. Right. Now let's see. This guy's coming in for the dive right here. Right. It's on B splash, which we just solved. B splash. We got 14.14 meters per second. So hold on to that number. Right? And then he came to a stop. I'm going to exaggerate this a little bit. Right? Maybe like down here. Well, I don't know. That's pretty close. Right. 2 meters down. I'll say y equals 2 meters. 2 meters down. Right? And guys, while he was coming to a stop, you think that, here's like a middle picture. You guys think there were some different forces on him, and there was maybe a net force that was slowing him to a stop? Right. Okay. Let's do a free body diagram on this guy right in the middle. I should have drawn this bigger. That's okay. I think we'll be able to make sense of this. Okay. Guys, what's one force on this guy right here? Tell you what. Here, I'm gonna assume some stuff here. Do you guys think this guy probably has a weight, mg? Mg. Right. Oh, wait, did they tell us his mass? Yeah, they said it's 65 kilograms. So if his mass is 65 kg, you guys know his weight could be about 650 newtons. Like that, right? Do you guys think there's also a force from the water? Right. Really, it's 2 forces. I'm going to lump them together. Did you guys just say buoyant force? You guys say, right? You guys think there's also, in addition to that, a drag force while he's in motion? That's probably related to, I got the poster right here. This one, right? Like you could apply the drag force, like as he's slowing down. Now this would be kind of tricky to navigate because the speed is slowing down all the time. But I got the density of water is 1,000 kilogram per cubic meter right here. Okay, so let's lump all those forces into just one giant force that I'm going to call force from the water. All right, so I'll do something like this: F sub W, or I'll spell it out, force from the water. Love that. So a combination of both buoyant force and also drag force. Okay, now this is just this guy in motion there. Okay? We got two forces. Right? Oh, notice I made the drag force from the water much greater than his weight. I mean, that would make sense too, right? The net force is definitely going to slow him down in a hurry. Right? Right, let's see what are these forces. Right. We split my paper here. This is going to be a multi-part process. Okay? Because I think what we're going to do here, guys, force for the trees, is that this guy goes from a really fast speed to how fast is he moving at the end? 0 meters per second. And that happens over some distance change. Oh, does that also sound kinematic? Do you guys think kinematic? Okay. Now the question that we're trying to answer is something to do with forces. We're going to have to figure out how much he's accelerating, slowing down, and then bring in his mass. I think that's a job for this poster right here. You guys think? Here, I'll point it out exactly. Isn't he going from a crazy fast splash speed to 0? It's going to 2 meters down in the water. That's this. It's going to be the third kinematic formula. I just rearranged it to solve for acceleration. Right? And then we'll cross this acceleration bridge because we'll have acceleration at that point. We know his mass. We can get actually, this is a net force. Right? Now, the net force is the difference between the water forces and his weight. So we'll deal with that later. Okay. You guys know this is really net force, right? And you go back and change this poster a little bit. Put the word net. Okay. All right. So one bit at a time here. Let's do it's going to be the third kinematic formula. Vf squared equals V naught squared plus 2ax. Right? Let's just go ahead and plug in the numbers for this one. Okay? His final velocity is how much? 0 meters per second. Okay, so that value is being squared equals his initial velocity was how much? 14.14 meters per second. I'll save those digits. 14.14, although it's crazy precision, but that's okay. Okay, we'll save our rounding for the end. It's being squared. Plus 2 times, we're solving for acceleration. And, ooh, guys, what displacement did this all happen over? 2 meters. 2 meters. Boom, boom, just like that. Okay. So 14 squared, so there's 200. So now we're back to 200. I can subtract that. Divide by 2 times 2 is 4. Okay, get acceleration is, let's see, minus 200 meters squared per second squared, all divided by 4, and that's meters. Okay. Acceleration is that 50 meters per second squared? And you could either include a negative sign or you could just write the word up, upward. Right, so up to you. You can either say negative 50 meters per second squared or 50 meters per second squared upward. No, oh, sorry, I don't know why I boxed that. That's not the final answer because that's not exactly what they asked. But that is an important middle step, isn't it? Important middle step. Ooh, wait, just my turn a little bit here. So if you're watching this video at home, try to bring some light. Actually, it's not too far off. It's all right. Right. There you go. That fits a little bit better. All right. So you guys good so far? Now we know how much this guy's accelerating. Here, I got a side question for you guys. You guys ever hear of like G-force? Like how many G's? Like you're sitting in a rocket. You feel the G's, right? Something like that. Right? So, guys, what does that mean? Suppose you're experiencing like 3 G's, right? Here's maybe an extreme example you guys may possibly experience. You may ever go to Epcot, go to a ride called Mission Space, right? All right, you definitely feel some G's on you, right? It's like a simulation rocket. Right. What is 1 G? Is that 1 Earth gravity? How many G's are you sitting in right now? 1. What if you were an astronaut halfway between Earth and Mars floating around? How many G's is that? That would be 0. 0 in space. 1 down here at surface of Earth, right? Guys, this guy slowing to a stop in a hurry. How many G's does this guy feel? If 1 G is 10 meters per second squared, 5. Can I do a little dimensional analysis? A little railroad tracks? Say 10 meters per second squared is 1 G. 10. Yeah, that's 5 G's, isn't it? Right? Okay, all right, so just a little side fact. All right, let's go finish this puzzle here. Let's go net force equals mass times acceleration. Okay. Well, we just got the acceleration and we know the mass. So the net force could be 65 kilograms and 50 meters per second squared. Well, I'll say up. I'll just write the word up. Okay. So let's see what put it all together. 65 times 50. I'm looking at net force is 30 to 50 newtons upward. Okay, that makes sense. Right. Instead of the negative, I just replace that with the word up. Okay. Oh, but we got one more step to go. There's one more part, because net force is actually the difference of the actual force from the water and his weight. Okay, so here we go. So this net force right here is actually the water force minus his weight. Okay, is that all right? Okay. And guys, if he has a mass of 65 kilograms, what is his weight equal to about? 650 newtons. So let's do that. So we're still solving for water force. His weight is 650 newtons. The net force has to be 3250 newtons so he can have this acceleration, so he can come to a stop and this distance, blah, blah. Okay. Right, last step, can I just add 3250 newtons plus 650 newtons? That should be the force from the water. So the force from the water, which again is a kind of a combination of both drag force and buoyant force, let's just push it all together, okay, is 3,900 newtons. Yeah, that looks right. That looks right there. There you go. Right. So here, let's solve the sort of backward. We got 3,900 newtons up, minus his weight down was 650 newtons. That gives you a net force of 3,250. I'm just solving it backward. Okay. If I divide by his mass, which is 65 kilograms, that gives me his acceleration, which was 50 meters per second squared. Got that, right? And then if I go back to kinematic motion, I can even go back to his splash speed if I want to. Right. So just trying to remind you guys, kind of pace back and forth, show you guys how to solve that. All right. There's our pause point right there. You guys have a good hurricane day. I hope I see you Friday, but I'll either see you Friday or Monday. All right. You guys have a good one.